Hello, everybody. My name is James McClendon. I go by JB. Currently working as a process engineer for the Mosaic Company. I'd like to share and kind of give an update and run through of a project I've been working on for the better part of a year and a half in my, kind of free downtime at work. I've been working on developing a Slurry pipeline modeler for a couple different reasons, and I'll dive into those as we go forward. And they're a little more useful to explain. So, starting off, I built out this form to actually build the model in Excel. I don't have Excel on my desktop computer, so we're going to have to look at it in Google Sheets. Regardless, this should get the point across. So you got to fill out four things here at the top. First off is your water surface elevation or your liquid surface elevation. Might not necessarily be water. Your suction depth, so if you have a suction lift system, how deep are you actually in this material? And then a final discharge elevation. Those three things kind of come together to give you your inlet suction pressure, your suction inlet pressure, and your static head across your system. And finally, in our systems, we have flush forward sealing in our centrifugal pumps. So we have water coming in at each individual pump. The values probably are not consistent. However, the model I use currently only includes a static value for sealing water at each pump. So we have 100 GPM coming into the pipeline at each pump. All right, moving on to the actual table where you build your pump and pipeline. So name is just a string. Type, also a string, but here you would select either pipe or pump. If you select pipe, it's going to ask you to fill out a couple things. The inner diameter in inches, the length in feet, the inlet elevation, feet as well. Roughness, this is like an absolute roughness value for steel, 5 times 10 to the negative 5 feet. And K value, this is like a minor loss coefficient, so it's going to be whatever you decide to use for your calculation. All right, if you select pump, you would then come over here to the pump information. You select a pump shell from a drop-down list. It's here in the pump data sheet. I'm not going to go there because some of the information I'm not sure is okay to share online. But essentially it has a table with these A, B, and C values as well as basis RPM and basis impeller and discharge diameter. So these things are A, B, and C are the A, B, and C coefficients of a second order polynomial regression. A lot of pump curves kind of look like a second order polynomial. You can get a decent fit across the flow versus head using a second order regression. Basis RPM and basis impeller are the RPM and impeller size that these A, B, and C coefficients are actually pulled from off a pump curve. And the model that we use needs a discharge diameter, so that should also be included as well. All right, over here, user inputs include the actual impeller and the max RPM. So these are things that you would put in. These will set the impeller and RPM when the code launches. So let's actually go into the code. As you can see here, it's being run in Octave. I coded it in Octave, so it's a .m file. Anybody unfamiliar with Octave, it's an open source MATLAB kind of clone. So it has a lot of calculation functions that MATLAB has. It does not have a lot of the simulation stuff, but for like numerical methods and matrix mathematics, it does a really good job. So to launch it, you just call the name of the .m file. So for me, it's PDSUS. PDSUS stands for Pump Design Startup Sequencer. Currently, I have not coded the sequencer, so in progress. When it launches, thank you for using this tool, record bugs, and submit to my work email, which I've omitted for the purpose of this video. So you can also see here this numerical solver was developed using the GIW 4-component method presented in the 4th edition text. We got a text, kind of top of the line, Slurry, pipeline calculations and methods from going to KSB GIW, a seminar up in Augusta, Georgia. I believe the name of the seminar was Transportation of Solids Using Centrifugal Slurry Pumps. They put it on every year. Excellent course. The people who wrote the text, they're there helping teach. Given the seminars and whatnot, it really is top notch. So if you have any interest in maybe building something like this yourself or understanding some of the workings behind it, I highly recommend looking to go to that next year. All right, and then put the name of the model within your Excel workbook and press enter. So I have one named demo. It's not going to look for demo. All right, and it launches the code, runs, parses everything, runs a calculation. Here we are. I wish I could say this was done, but we're going to hit calculate system one more time. Here we are. So this is what it should look like. Now we have our pressures, suction and discharge pressures at each pump. Just a brief overview of the window. Yeah, 1980s called. They want their GUI back. Unfortunately, I'm not a coder by trade. There's an old joke. It's like an engineer can build a bridge that can barely stand. It turns out an engineer can also build a code that will barely run. And that's kind of what this is. But it works pretty good, comparing it to other modelers. So, hey, beggars can't be choosers. So up here in the top left, the solids inputs, this is where you can set your solids concentration delivered, so the percent solids out by weight. So you can set that using this slider here. Some particle size information, so D50, D85, D100. And if you're using the auto regression, so it uses a Weibull distribution function parameter with your given D50, D85, it calculates what D100 should be. The graph settings, so this will tell it to either show the pump and system curve or the pressure profile. Pressure labels, this used to turn these on, it does not anymore. I just have them auto-generate because I made it a little quicker. Print plot, this will print the plot if you need to, get an image to deliver for a report or something. Up here at model results, this will tell you your suction inlet GPM and discharge GPM. So knowing the suction inlet GPM or discharge GPM, you can calculate the other one through the sealing water multiplier. And finally, tons per hour delivered. So this is ton solids delivered based on GPM out and percent solids by weight delivered out. Moving down south, the table information, so that is this table down here. So currently I have pump information, so it's showing all my pump stuff, is it on or off, what the name of the shell is, what RPM is it, what size is the impeller, and what is the calculated percent solids by volume in the pump. So currently that is inconsistent with the percent by weight out. I need to, cut in a conversion, but at the moment, unnecessary for my use. This can also go to pipeline information, where we have diameter, length, roughness, K value, CV. Currently, the top four are not editable, so if you change it and run it, it'll kick it back to what it was. Really, all the edits should be made in the worksheet because any edits you make here will not get written to the worksheet. So I'm trying to avoid, making changes here specifically because it does not have the back right functionality. All right, so I'm going to change my D50 to like 230. It says 230 micron. These are all in micron units, and maybe change my percent solids down to 32%. And now I hit calculate. So our particles got smaller, our solids went down. I would expect our flow rate to increase here. So from 16,366, let's see. Yep, so we went up to 19,207. Our pressure is adjusted accordingly. And this is kind of how the typical slurry line modeler works. You set your particle size parameters and then you tell it what the percent solids out is. And then based upon that, it says, okay, my percent solids out is 32%. That means everything in this part of the pipeline here, past the last pump is 32, minus 100 GPM sealing water. So now my percent solids here needs to change. So if we look and actually see, our pipeline information, we go from 0.1504, go through a pump, 0.1512, go through a pump, 0.1520. So it's kind of consistently increasing because we're removing sealing water from the equation, right? However, it always increases. So under this current extrapolation, well, not extrapolation, but calculation, your suction inlet is going to be much higher. So 0.16 versus 0.15, right? Like 0.01 doesn't seem like much, but when you're on the cusp of settling out or something like that, it could be considerable. The effect of this is also increased at lower flow rates, like maybe closer settling velocity of your slurry. this gap between the two might be larger because the effect of the sealing water opposed to the total flow is much larger. That's a problem. In a lot of processes, your percent solids are not uniform. For example, a pumping system that's pulling out of a mining pit. So you have a very inconsistent value of percent solids coming in. So to assume that your percent solids here are a value to give you a percent solids there might give you very misleading results in the middle of this thing, right? So under percent solids model, I have user solids input. If you switch to this, and I don't know exactly what the difference in the calculation is, so it went from 17,707 to 17,755. As far as I can tell, it should be the exact same calculation. I think there's some rounding or something going on, but it's close enough, like 50 GPM, whatever. Doesn't hurt me. But now we'll see as we change percent solids up here, I mean, even if we go like huge, right? This doesn't change. So we're no longer controlling the model with solids out. We're controlling the model by setting the percent solids in the table. So here's our current pipeline, right? What would it look like if I didn't have percent solids past pump 5? Maybe I started up, I was purging clean water, and I start loading it with solids, right? So in the pipeline, 5 onward is 0, and in the pumps, let's go 5 onward is 0. Would we expect considerable change? Let's see. Oh man, our pressures tank, right? So what's going on here? Flow rate increases. Geez. Flow rate increases. Sorry, my headset cut itself off. And our pumps are not making as much head, not only because they're pumping faster, but because they're pumping clean water. Lastly, the static head consideration in this pipeline, we have a very large rise to the discharge. It's coming to the top of the plant. All that is no longer nice, heavy slurry. It is standard water. So all that back pressure we were getting is gone. And now we start seeing some very like crazy trends going on, a lot closer to real process data existing here. Now, what if we're pumping on like all clean water, right? So much more normal trend. All right, I start sucking in solids. Let's say I get solids all the way to MLP 11. Oh man. So a lot of tank here, right? We have a very high percent solids between this section. Flow's still high because solids haven't worked their way down yet. You know, we're seeing kind of the truth behind maybe some of the problems that you can see in an inconsistent feed and long slurry pipeline coming to a head here. So now I go all the way to 5. All right, solids work their way. Pressure's recovered here, but now they're dropping in the middle, right? Okay, solids are, let's say they work their way all the way to MLP2. Okay, now the pressure's on the suction end are recovering, but we're still a little low on the discharge end. And finally, as these solids come through, we're back to something more normal. All right, and now let's just take a quick look even at like the opposite. So I start sucking up, what is this, up to 13. So I start sucking up water. All right, so pressures are dropping here. Everything down the stream dropped, right? I'll go all the way to 9. All right, water's coming through. Our solids are working their way out. Oh man. Oh geez, right? So now we're getting this like pressure wave occurring in the middle. All right, let's go to 5. 6 to 5, okay. All right, that pressure wave is working its way down the pipeline. It might be opposite actually. working its way down the pipeline. We're getting very high over here. We're not building a ton here. All right, let's go all the way to 2. All right, regulating. And now we're back to normal. So we can see, like, I don't know what values you point to here, but let's take a look real quick. So if I said, man, I got 0%, it looks good. I think it's close to like 40%. Yeah, I got 40%, it looks good. But like getting there could be terrible. So that's kind of why I try to code this, is so that, we can see some of the more transient behavior of the slurry pipeline as solids comes in and solids leave, as well as, what if I have a really big density wave come through? Because that can exist in our process. So that was kind of the purpose of making this. And then I said, well, if I can take a snapshot of this and get a flow rate, I should be able to guesstimate a state moving forward. So that's kind of the next step of this whole thing. What happens if I take these pipes and I make them really small? So I'm trying to build like a finite element analysis modeler here. Significantly slower, but essentially this thing is a model. And when you look at the pipeline information, so now I've changed it to 100-foot sections. So there's a ton of 100-foot sections between everything. It's like in the order of hundreds. So you could set boundary conditions. So if you set the percent solids in each section at the start, you set a percent solids in. This isn't done yet. I'm just speaking out loud here. Set a percent solids in. Then you could say, okay, at this current state, my flow rate is this. How many sections change in X time? Put it forward. If you know your stuff coming in, you can set that, back at the suction here and into these pipes. If you know your sealing water flow, you can dilute and move it forward, and then you get to your next state and get the flow rate there. And essentially, what you can kind of do is try to create a, FEA simulator. It's not going to be exact, but you could say, okay, I have no water. I start sucking up this percent for X time, percent solids, and then I switch. I'm now sucking up X percent at this time, and eventually, you could get something kind of cool going here. You could almost have a simulator, like a time-based simulator. So that's the next step, is to try to extend this into a simulator. And let me see, this takes like about 5 seconds to run, I think. So even though it has all these sections, it might be closer to like 7 at that point. Yeah, 6.5. So it's still putting out a ton of stuff to the right, which anybody who's done code knows that like writing to the command prompt takes a fair amount of time. So that might be able to get down to like 6 seconds. But if your time step is bigger than 6 seconds, the good news is you can see the future, um, which is pretty cool. But yeah, that's it. So completely done open source. Most of the code's in Octave, and then the setup is here in Excel. The other good part is that you can input kind of whatever pumps you want. So if you get all these values, you can input into a table and have them selectable. Currently, I just have the major ones that we use in our process. But give me your thoughts. Let me know anything you think I should change, or where my thought process might be wrong. I'd be interested in hearing from people who also work in slurry transport. Thank you.